In this video, we'll be discussing the process of making simple organometallics and their importance in organic chemistry. Organometallics are extremely useful in making new carbon-carbon bonds. Their main job is to act as nucleophiles that attack electrophilic centers. They are powerful nucleophiles because of the extreme polarization between their carbon-metal bonds. We have learned that the more electronegative an atom is, the more it tends to attract electron density. When comparing the electronegativities between, let's say, carbon and oxygen, we see that oxygen is more electronegative than carbon. Therefore, most of the electron density is pulled towards the oxygen atom. Organometallics are extreme cases where there is a bond between a metal and carbon atom. Now, carbon is the one that is far more electronegative and therefore pulls most of the electron density. The greater the difference between the electronegativities between atoms, the more polarized the bond becomes. This ultimately means that there is a much greater difference between the attraction of the bonded electrons within the compound. In extreme cases, complete polarization happens, which creates ionic bonds. The polarization of a carbon-metal bond is pretty significant, and since electron density is pulled towards the carbon, we can think of the carbon as basically possessing a lone pair. The partial negative charge makes this carbon a powerful nucleophile that can be used in reactions and provide ways to make new carbon-carbon bonds. Now it's time to look at how to make organometallics in the lab. One special type of organometallic is called a Grignard reagent. Magnesium turnings like the one shown here are reacted with alkyl halides and ether solvents. The solvent of choice is very important, and we'll explain why in just a moment. The mechanism for this reaction, however, is still relatively unknown. It basically involves the insertion of magnesium between the carbon-halogen bond through a redox reaction. It's called oxidative insertion because the oxidation state of magnesium changes from 0 to 2. It becomes more stable with this increase. When choosing an alkyl halide for the magnesium to react with, the compound must not contain any functional groups, with the exception of acetyl groups. The reagent's strong nucleophilicity will immediately attack those functional groups. Once we've created our Grignard reagent, it becomes a very powerful nucleophile. More specifically, electron density is pulled towards the carbon, and the magnesium halide simply becomes a spectator during the reaction. Grignard reagents are so powerful, in fact, that they must be kept free of any moisture. That is why we must use ether solvents when making Grignard reagents. Ethers are non-acidic or aproducts and unable to protonate the reagent. Furthermore, they help stabilize the magnesium cations by solvating them. The carbon nucleophile deprotonates nearly anything and is utterly destroyed in the presence of moisture. Therefore, in order to keep the reaction free of any moisture, steps such as baking glassware until dry and adding indicators such as calcium chloride during a reaction are necessary steps as well. Another type of organometallic is the organolithium reagent. These react the same way as Grignard reagents but are made in a slightly different manner. It requires 2 atoms of lithium for every 1 alkyl halide present in the reaction. An observation you may notice is that the halogen is kicked off and lithium takes its place. Lithium's oxidation state goes up by 1 and the reaction takes place in ether solvents as well. The addition of organometallics to carbonyl compounds is probably the most straightforward way of making alcohols containing new carbon-carbon bonds. There are 3 main steps when making alcohols with organometallics. The first, of course, is making the organometallic itself. The second will be the nucleophilic attack on the carbonyl group, and the third will be a protonation of the oxygen atom. Let's break down the mechanism. The carbonyl compound, in this case an aldehyde, is a viable electrophile since oxygen pulls negative charge away from the carbon bonded to it, giving carbon a partial positive charge. From what we've already seen, the organometallic, a Grignard reagent in this example, is an extremely strong nucleophile and only makes sense that it adds to carbonyl compounds. This is a prime example of a nucleophilic attack at the carbonyl group. As the Grignard reagent is added to the electrophilic center, the carbon-oxygen pi bond breaks and its electrons are moved onto oxygen. We now have what is called an alkoxide before the oxygen is protonated in the second step with the introduction of water. From this reaction, it looks like we've created a secondary alcohol with a new carbon-carbon bond. Just to note, the same mechanism applies when working with organolithiums. Here's another example using organometallics. The addition of these reagents to solid carbon dioxide forms carboxylic acids. Again, the mechanism should be similar to our previous example. The organometallic, again in this case a Grignard reagent, is highly nucleophilic and attacks the electrophilic carbon and carbon dioxide. This gives the carboxylic salt, and once an acid quench occurs, the Grignard reagent is destroyed and the oxygen is protonated. Notice how the bond between the oxygen and Grignard reagent collapses and forms a double bond with carbon and oxygen, while the carboxylic salt's once pi electrons now form a new oxygen-hydrogen bond. Now we've learned how to prepare some basic organometallics. Just to recap, these are nucleophiles that are ideal in making new carbon-carbon bonds. The most standard usage of organometallics is the reduction of aldehydes and ketones into alcohols and carbon dioxide into carboxylic acids. This video merely scratches the surface of the vast field of organometallics. A whole area of research in organic chemistry is devoted to the study of these carbon metal compounds. Hope you enjoyed this video. Thanks.